Section number 2 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Blaine Aidan McCoy, Riverside, California, 2019. Energy. The law of conservation of energy. We have now gone as far as we conveniently can in considering the intertwining strands of the atom and of electricity. It is time to turn to the third strand, energy. To physicists, the concept of work is that of exerting a force on a body and making it move through some distance. To lift a weight against the pull of gravity is work. To drive a nail into wood against the friction of its fibers is work. Anything capable of performing work is said to possess energy, from Greek words meaning work within. There are various forms of energy. Any moving mass possesses energy by virtue of its motion. That is, a moving hammer will drive a nail into wood, while the same hammer held motionlessly against the nail head will not do so. Heat is a form of energy, since it will expand steam that will force wheels into motion that can then do work. Electricity, magnetism, sound, and light can be made to perform work and are forms of energy. The forms of energy are so many and so various that scientists were eager to find some rule that covered them all and would therefore serve as a unifying bond. It did not seem impossible that such a rule might exist, since one had been found in connection with matter that appeared in even greater variety than energy did. All matter, whatever its form and shape, possessed mass, and in the 1770s, the French chemist Antoine Laurent Lavoisier, 1743 to 1794, discovered that the quantity of mass was constant. If a system of matter were isolated and made to undergo complicated chemical reactions, everything about it might change, but not its mass. A solid might turn into a gas. A single substance might change into 2 or 3 different substances, but whatever happened, the total mass at the end was exactly the same, as nearly as chemists could tell, as at the beginning. None was either created or destroyed. However, the nature of the matter might change. This was called the law of conservation of mass. Naturally, it would occur to scientists to wonder if a similar law might hold for energy. The answer wasn't easy to get. It wasn't as simple to measure the quantity of energy as it was to measure the quantity of mass. Nor was it as simple to pen up a quantity of energy and keep it from escaping, or from gaining additional quantity from outside, as it was in the case of mass. Beginning in 1840, however, the English physicist James Prescott Joule, 1818 to 1889, began a series of experiments in which he made use of every form of energy he could think of. In each case, he turned it into heat and allowed the heat to raise the temperature of a given quantity of water. He used the rise in temperature as a measure of the energy. By 1847, he was convinced that any form of energy could be turned into fixed and predictable amounts of heat, that a certain amount of work was equivalent to a certain amount of heat. In that same year, the German physicist Hermann Ludwig Ferdinand von Helmholtz, 1821 to 1894, advanced the general notion that a fixed amount of energy in one form was equal to the same amount of energy in any other form. Energy might change its form over and over, but not change its amount. None could either be destroyed or created. This is the law of conservation of energy. Chemical energy. There is energy in a piece of wood. Left quietly to itself, it seems completely incapable of bringing about any kind of work. Set it on fire, however, and the wood plus the oxygen in the air will give off heat and light that are clearly forms of energy. The heat could help boil water and run a steam engine. The amount of energy in burning wood could be measured if it were mixed with air and allowed to burn in a closed container that was immersed in a known quantity of water. From the rise in temperature of the water, the quantity of energy produced could be measured in units called calories, from a Latin word for heat. The instrument was therefore called a calorimeter. In the 1860s, the French chemist Pierre-Eugène Marcellin Berthelot, 1827 to 1907, carried through hundreds of such determinations. His work, and similar work by others, made it clear that such chemical energy, the energy derived from chemical changes in matter, fit the law of conservation of energy. Here's how it looked in the last decades of the 19th century. Molecules are composed of combinations of atoms. Within the molecules, the atoms stick together more or less tightly. It takes a certain amount of energy to pull a molecule apart into separate atoms against the resistance of the forces holding them together. If, after being pulled apart, the atoms are allowed to come together again, they give off energy. The amount of energy they give off in coming together is exactly equal to the amount of energy that they had to gain before they could separate. This is true of all substances. For instance, hydrogen gas